right? Before that, we've touched on linked lists as well, which are just a bunch of nodes linked together, right? So for trees, it's also being comprised of nodes. But for trees, of course, there are different types of trees, but for the trees that we are talking about today, each node could have two children, one right or one left. Right, so this is what you call a binary tree. Okay. And here, what we have here is actually a BST, which is a binary search tree. So binary trees are trees with nodes that have two or less children. For binary search tree, it's a special type of binary tree where for each value, okay, so for example, if the value here is 5, okay, then the value to the right would definitely be smaller than the value, the value to the left would definitely be smaller than the current value. So this could be 4 or 3 or 2, maybe. Okay, and the value to the right must be larger. So this could be 7, 6, 9, or whatever. All right, so this is binary search tree, and the principle is same for the rest of the nodes as well. All right, so me now? Am I back?
Yeah, we can hear you, but it doesn't look like your screen is working though.
Sorry? My screen is working?
Yeah, I can't see your screen.
Oh, okay, let me reshare it. Technical difficulties. My bad. Okay. So where have I stopped? So basically, I'm talking about a binary search tree is a variation of a binary tree. But for binary search trees, for each node, if there is a node to the right, which is the children to the left. Sorry, if there is a children to the left, then the value of the node to the left must be smaller than the current root. And if there is a value to the right, then the value must be bigger. So this is the rule for binary search trees. Okay. And we can look at the question. So we are given a binary search tree. So we can take this example and you can see that right, so this is an example of a binary search tree. for every value, the value to the right is smaller and the value to the left is larger, right? So there's no value to the left of 15, but if we look to the right, it is larger than 15, which is 18. Same for here. The left of 5 is 3, the right of 5 is 7. Okay, so with this binary search tree, the question wants us to return the sum of the values of all nodes within the value of low and high, inclusive. All right, so if low and high is 7 and 15 in this case, then I would have to return 7 plus 10 plus 15, right? So this is the range, and I have. So of course, what we can do is we can traverse the whole tree. Right? So that would take us O of n. There is one thing that we can do to decrease the complexity by a bit, but it would still be O of n. It's just that it's like a bit lesser than O of n, where we can cut off those that are out of range. Okay, so for example, let me just write some pseudocode. Okay, so here, right, what we can do is we can traverse the whole tree. And then, while traversing the whole tree, I will check each value. Okay, and if the value is within the range, okay, I think I have some messages. Oh, can you hear me? Is it still super laggy? I apologize about that. Let me try to fix this. Can you hear me better now? I switched Wi-Fi's. Okay, yay. Now, where was I? Okay, so traverse the whole tree, and at each node, I will check the value, and if it's within the range, I will just add on to the sum, right? So I can keep like a global variable called sum. So I would just add to sum, right? And the other thing that I can do is, if the value is, okay, so for example, right here, if I'm already at 15, okay, and I know that high is 15, maybe I can go to Jamboard. Okay, so if I'm already here, right, and I know that the high is 15, then there is no point of me moving to the right anymore, right? Because if I move to the right, it'll only be larger than 15, but 15 is already a maximum. Okay, so I can just cut off here. Okay, so what we do is we can check for the maximum or minimum and see if we want to continue searching. If we want to continue searching. So this is my logic behind this. And okay, let me just check the chat. Okay, everything's good. So this is how I'm going to go about, right? And traversing a tree, there are two ways you can do it: recursively or iteratively. So usually people would do it recursively. So I'm going to do it recursively today. And if we have time, we can try to implement it iteratively. All right. So again, let's just create the code right now. Okay, again, I'm using C++. Should be quite easy to understand. Everything is very how to say, everything is very basic, like it looks very simple, the syntax I mean. So here I'm just making a private variable because this is a class, but yeah. Okay, so the variable, I'll just call it sum, and I'll initialize it as 0. Okay, now here what I can do is I can do a recursive depth first search to go through all of the nodes, right? So I'll just make a depth first search function. Right, so depth first search meaning that I would go like this. This, like this. Okay, so doing the depth first search, I'll take in the same parameters as range sum. Okay, and then I have messages. Why 15 is highest? Oh, so this is actually the question. It's given in the parameters. So I'm given root, low, and high, and I need to return. Okay, so looking at the prompt, I'm given low, high, and root, and I have to return the sum of values of all nodes with the value in the inclusive range of low and high. So 15 is given by the question. Okay, so yeah. So okay, I will not implement this first. I will just do a depth first search that will traverse the whole tree just to, let you see how it looks like. So it's super simple. You just establish a function, and then you can search for the left and the right node. Okay, so I can just search for the left node. Okay, and I can also search for the right node. And again, for recursive functions, we have to have a base case, right? A terminating case. If not, it will go on forever. So if the node that I'm traveling to is null, is empty, it's nothing, right? Meaning that, for example, if I'm at 15 and I go left, it will be null. So if it is null, then I will just stop recursing. Okay, so if the root is null, then I would stop recursing. Okay, so this is like a simple template for me to traverse through all of the nodes. Okay, now if you look at the first step, I will check each value, and if within the range, I will add to sum, right? So I can just check the value. If root, okay, so if the value of root is more than equal to low and less than equal to high, right? Meaning that it's within range, then I would just add on to sum. Okay. So this could be our solution. And then up here, we can just return sum. And we also need to do the initial call for the depth first search. And I will just put root in. So this is the first call. And then I will go in here and I'll recursively search for all of the children. Okay, so if we look at this second thing that I wrote, we can check for the max and min if we want to continue searching, right? If we are already at the max, then there's no point for us to keep going to the right. So what we can do here is we can say if the value of the root is more than low, meaning that there is a possibility that we can go even lower, right? So we can continue to go lower to the left. Okay, and then if the value of the root is less than high, meaning that there is a possibility that we can go higher, so we can check to the right. Oh, I forgot to change this. So I need to change this to right. Okay. And this would be our overall solution for the recursive method. We still have 10 minutes, so later we can try implementing the iterative way. But for now, anyone has any questions? Let me check the chat. Okay, I think no questions so far. So let's try to run this and see if there's any issues. Okay, yay. So this is how we can implement this recursively, right? So let's try to do this iteratively. Okay, so for recursive functions, right, we are using a recursive stack. Now we need to, since we are doing it iteratively, we have to create our own stack to replace the recursive stack, right? So with that, okay, let me just I'll just copy this out and okay. Okay, so let's do this iteratively. If everyone's following me, right? Okay. So we're gonna try to implement this iteratively, and as mentioned, when doing this iteratively, we would have a physical stack to replace the recursive stack. All right. So I'm just gonna create the stack first. Oh. Stack. Okay, and I would store a tree node in the stack. Okay, you will see why it's a tree node and not the integer later. I'll just call this stack the num stack. Okay, and again, same here, we would have an integer we call sum that we can record the sum. I hope that you can see my, oops, too big. Okay. So we have this. All right. And first of all, what we do is we push the root into the stack first, and then we can do a while loop while the stack is not empty. Then we will continue to search for the children. Okay. So this is also how breadth first search kind of looks like. But breadth first search, we use a queue, right? It's kind of the same, but not really. Okay, I don't know what I'm talking about. Sure. But I'm pushing root into the stack. Okay, and then now I can do a while loop. So while the stack is not empty, okay, so not empty meaning that I have to add a not in front. So while the stack is not empty, I can traverse its children's, right? Okay, so here, it's almost the same as our depth first search approach. Okay, if we look at our depth first search approach, what we are doing is we are recursively calling the function again and again, right? Using the next nodes. But now we're doing it iteratively. What we can do is we can push it in the stack first, and later on when we retrieve it from the stack, we can check it. All right? So the stack is kind of like a place where we can temporarily put the nodes that we want to check later. Okay, so here we can get the values out of the stack. So let me just put this up here. Okay. So we are going to pop the node from the stack first. I'll just call this node the current node. So car. Okay, current equal to the top of the stack, right? Okay, and then after I get the node from the top of the stack, I can just pop it off of the stack. So num stack dot pop. Okay. I don't know why I keep getting notifications, but when I check the chat, there's nothing. Okay. So I'm popping it off the stack. So here I'm getting the first element from the stack. Okay. And then the next thing I can do is I can do the checkings, same as the one we did in the defer search. So I can just copy these actually. And I can put it here. Oops. Let me. Okay, so these are the 3 checkings that we do. The first one is to check whether we want to add it to our sum, right? Okay, so here we are using current because we are checking for the current value. And here we are checking if we want to continue to traverse the children's, right? But since now we are not using recursive function, so what we can do here is we can push it onto the stack so that later on we can pop it off and check it. Okay, so it's kind of like somewhere we can temporarily store it first. So what I can do is I can just push it onto the stack. Okay, so here I'm pushing root to the left onto the stack when the value of current is more than low. And there's also one more case that we need to take care of. Like, what if there's no left anymore? Then we are just pushing null values, right? And we are pushing null values. Somehow we are trying to access the null values. So this would give us some error. So either we can do the checking here, or we can do the checking like when we pop it from the stack, we can just check it if it's empty. But I think I'm just going to check it here. So if the current value is more than low and the left of current is actually exists, there's actually a node at the left of current. Okay, so in this case, then I would push the left node into the stack. Okay, and I'll do the same thing for right. And then this would be the same as well. So here I am actually pushing onto the stack instead of calling the function again. Okay, and our function should be done. So this should work, right? And at the end of everything, I would just have to return sum. Okay, let me take a look at this function, this solution one last time. Okay, so there is one edge case. What if the root that they give us is actually null? So we have to do that as well. We have to check for that. So it's just a simple edge case that we can do. If the root is null, then we can just return 0. Okay, let's just run the cases to see. Within block comment. Okay, there's something wrong with my. Is it this? Does it have to be? Okay. Maybe I need to wait. Oh, there's 2 of these. Okay. So there's a wrong answer. Let's try to debug this. Okay. So since I'm using a stack, right, I should be putting the right first and then the left, so that the left will go on top. Maybe this would be it. Okay, and then if the current value is less than high, right, and the current is the current to the right exists. Okay, here, since if we look at the question, it says inclusive range. So I have to include it as well. Let me see. No, actually not necessary, because if it's the same, then the one at the right would be more than it. Okay, let's just try this first. Okay. Maybe it's this. I'll just try with the why is it that all my output is 30? Return sum. So if root is invalid, then I return 0. And then sum equals to 0. Then I have a stack. Then I push root to the stack. Okay, and then while stack is not empty, I would pop off the top to be current. I pop it from the stack. And then if the current value is less than equal to low, and no, more than equal to low and less than equal to high, I would just, I'm using root here. So I have to use current because I am popping off the current node. So actually this shouldn't matter, the equal, as I've mentioned in the logic. If it's equal to 15 already, then like why even go to the right? Okay, so let me try to run this. Okay, so this should do the trick. And yeah, actually I spent like maybe 2 minutes doing the debugging. I actually wanted to show you how it would work iteratively. Maybe I can do it quickly. Okay, so I'll just do this quickly. So this is my stack. Okay, at first I push the root into the stack, so 10 is here. Okay, and then I get into my while loop, right? So while the stack is not empty, I will pop this off. Okay, so 10 would be popped off to be current. So current would be this. Okay, and 10 is not in the stack anymore. So this would be current, and then I would check if it is within the low and high. So the low is 7, the high is 15. So since it's within the low and high, I would add it onto sum. So sum would equals to 10. Okay, and then after that, I will check for the left and right, right? So if 10 is okay, so if 10 is more than low, which is true, 10 is more than low, and 10 to the left exists, which is this one, right? This node exists, so I will put it into the stack. Okay, and then same logic, I will put 15 into the stack. Okay, and then that while loop would be done. I will go into the next iteration where I will pop off the top of the stack, which is 15. So 15 will be popped off. Okay, so this is why I have to store the nodes instead of the integer, because I need to access its pointers. Okay, so now current is 15. Okay, and then I will check if it's within the range of 7 and 15, which it is, right? So I would add on to our sum. Okay, and since 15 is not less than high, so I wouldn't put 18 onto the stack. Okay, and since 15 has no left node, so there's nothing for me to put in the stack as well. Okay, so the next iteration, I'll be popping off this 5. So now current is 5. Since I've already popped off 5. Okay, and then since 5 doesn't satisfy the condition of between 7 and 15 inclusive, So I don't add 5 into the sum, okay? And then I check, okay, if 5 is lower than 7. So since 5 is already lower than 7, there is no way that we would need to check here, okay? However, 5 is lower than 15. So there is a chance that we could still go right. So I will add 7 into the stack. Okay. And then the next iteration comes. I would pop 7 off of the stack. Okay. So now this is the latest current. And then, okay, 7 is the latest current, yeah. And I would check if it satisfies this condition of between 7 and 15 inclusive. Since it satisfies it, right? So I would just add on to the sum. Okay. And I would like check if there's any children. Since there's no children, so I won't add it onto the stack. Okay. And here comes the next iteration. So the stack is now empty, right? Remember our while loop, our condition is while the stack is not empty. So since the stack is empty, I would exit from the while loop and I will just return sum, which is 10 plus 15 plus 7, which is 32, which is our solution. So this is how the iterative method works. And yeah, I'm already over time. So I hope you guys don't have any questions. If you have, you can put it in the chat and I will like type the answer for you. And now we can move on to the next question. Thank you everyone for joining us.
Okay, great. So for the second question, it wouldn't be as hard lah. We're not talking about binary trees today. For the second question, it's actually quite easy. Still arrays. Still talking about arrays. But this time it's something more interesting. It's a bit similar to what last week Racing has told you all. I think it touches one of the concepts. So this kind of arrays is a special array, special type of array. It's what we call a mountain array. So basically what's a mountain array is where all the numbers at first, from the first index to the last index, so there exists a peak. So let's just list out like the condition. So let's just list out the conditions. So we know that the first condition is where there must be a peak. There must be a peak. So why do I say what is a peak? So like if you imagine mountain is like a triangle, and then there will be like a highest point. Like for every mountain there's a highest point. Genting Highland or Himalayas, there must be a highest point. So there must be a peak for a mountain to exist. That's why when we say mountain array, there will always be a maximum element. And then the peak, it must be sharp. Okay, we say that the peak must be sharp. That means I cannot have like 0, 2, 3, 5, 5. If I have like 0, 2, 3, 5, 5, the peak would not be sharp, it will be flat. Like this 4 will become, if you imagine this 4 is 5, then it will be like a flat line here. So that will not be a valid mountain array. So every valid mountain array looks like this. From the first index to the peak, it will be strictly increasing. And then from the peak to the last index, it will be strictly decreasing. How to say strictly increasing is that the next element cannot be equals to the last element. I cannot have like 0, 2, 3, 3, 5. Like you look at this example, right? So a valid one is 0, 2, 3, 4, 5. An invalid one is a 0, 2, 3, 3, 5. So I cannot have like repeated elements. I cannot have them the same because this is still increasing, but it's not strictly. Strictly increasing means I cannot have repeating elements. So here actually the graph, this visualization is actually quite good. We understand what the problem wants in the first place. So we know the conditions. There must be a peak. And then the second condition is where before the peak, it must be strictly increasing. And then after the peak, it must be strictly decreasing. So these are the few conditions that we know when we first look at this question. So there's also one cases. Let's say is this a valid mountain? So let's say 0, 2, 3, 4, 5, 2, 1, 0. This is exactly the same one for the example. So this is a valid mountain array because 0, 2, 3, 4, 5, reach the peak, and then it start decreasing 5, 2, 1, 0. So the question is, what if we have an array like 3, 4, 5, 6, 7, 8? Okay, 0, 2, 3, 4, 5, 6, 7, 8. Reach the peak. We reach the peak. But the problem is, if the peak is the last element, the third condition is not met. So this condition is not met if the peak is at the last element, because there's nothing as after the peak, because the peak is the last element. There's no after the peak. So this is invalid because does not meet criteria number 3. Criteria number 3. And then let's make an example. Let's reverse this array. 8, 7, 6, 4, 3, 2, 0. So let's look at this. So we have 8, 7, 6, 5, 4, 3, 2, 0. So basically here, the 8 is still the peak, but the peak is at the beginning of the element. So it doesn't meet criterion number 2, sorry, because we say in the criterion number 2, we say before the peak, it must be strictly increasing. But the problem is the first element is the peak, so in front of it there's nothing left, so there's no such thing as before the peak. So these two are invalid. And looks one more for invalid case. Let's say we have 3, 5, 5. Okay, this is also invalid. It doesn't meet criteria number 1. Criteria number 1. Why? It's because there's no peak. Because like 0, 3, 5, 5, and the 5 and 5 is flat. It's not a peak. We don't have a peak. We don't have a peak here, so it doesn't meet criteria 1. So as long as we know these 3 criterias, or call it conditions lah, then we can solve this problem very easily. So imagine how we can solve this is where, imagine you are a person, right? You are a person. You start at 0, at index 0. You start at index 0, and then you walk up. Okay, you walk up until you reach the peak, then you walk down. So at each iteration, every time when we try to take a step forward, so when we take a step forward, we check for these 3 conditions. If all these 3 conditions is met, it's still valid, we move on 1 step. It's still met, then we move on 1 step until we reach the very end, and then we just check whether the person has finished walking the whole mountain. So if the person finished walking the whole mountain, then this is a valid mountain array. If the person stops halfway and it cannot continue because the condition is not met, then it's not a valid mountain array. So how to check that? So let's just give an example. Let's say I have an array like this: 0, 5, 5, 4, 3, 2, 1. Okay, so we just go through. So at first I'm here, right? I'm at 0. So we don't know whether there's a peak yet, but we can keep on. We know the second condition is met because the next element is larger than the 0th element. So okay, so we keep on going. So we go, and then we add element number 2. Then we check, okay, is this condition met? So we do not know whether there's a peak or not yet, but we can check the second criteria. We say, okay, so we check the next element is larger than the previous than the current element. So this is still true. We move on. So move on until 5. So we does not know this is a peak or not yet, but we can check for the second. We can still check. We can check for the second criteria. So the next element is 5. The current element is 5. So is it strictly increasing? No, it is not strictly increasing. So we cannot move on. So we cannot move on any step further. So we just stop here, like we call it abort mission, and then we just return false. Alright, so this is how we're going to do it. Then let's say let's give like a valid test case. So 0, 3, 5, 6, 4, 3. So let's do it again. So we start from 0. Then we know, okay, so next element is larger than current element. Okay, we move. Then at 3, next element is larger than 3. Okay, move on. Okay, then next element 6 is larger than 5. Then we move on. Okay, then we at 6. Okay, now we at 6. Then we check whether the next element is larger than the current element, and it is not. It is not larger than the than the current element. However, it is smaller. It is smaller. It is strictly decreasing after this point. We know that 4 is smaller than 6, so we assume we found the peak. So we assume the peak is equal to 6, because the next element, it's smaller than the current element, so we know that 6 is the peak. So we move on, but we switch the condition. Now we switch the condition where the next element always has to be smaller than the current element. So we at 6, we move on. So we check, is 4 smaller than 6? Yes, so we move on. Then we check, is 3 smaller than 4? Yes, we move on. Is 2 smaller than 3? Yes. Then is 1 smaller than 2? Yes, then we move. So now we reach the end. There's no next element already. So now we just make a check whether the person is at the last element. So yes, correct. The person is at the last element. Then we say it's complete mission, returns true. So basically this is the idea. We just have to implement this in code. So these 3 condition is the most important one. And one more thing. So let's just implement it. So let's say we have a person trying to walk up the mountain. So we assume I is the person. I is the person. So we always start at the 0 index. So we are going to index the array. So we always start at the 0 index, which is 0. So let's check. Let's see first. We do not know whether there's a peak or not when we first start out, because we are locking it one by one. So but we can follow the second criteria, because we start from before the peak. So we know that before the peak, it must be strictly increasing. So let's just do that. Let's just say, array I plus 1 is bigger than array at I, then we do I plus plus. Okay, this is basically we want to walk up. We want to walk up the mountain. We check whether the next element is bigger than the current element. So if the next element is bigger than the current element, okay, we just move one step forward. So basically it's like this idea lah. 0 is bigger than 3 is bigger than 0, so we move one step to 3. So we keep on walking up the mountain until we reach a point, until we reach 6. Okay, at this point, this condition is no longer true. Like the next element is no longer bigger than the current element. 4 is no longer bigger than 6. So then we know we reached the peak. We reached the peak because this condition is not met already. So we know we reached the peak. But there's few things that we have to check. So there's 2 things that we have to check when we reach the peak. We have to check if the peak is the last element. It's not true. It's invalid. And if the peak is the first element, it's also not true. So let's just do that. So we say if I is equals to 0, which is 0 means the first element. If I is the 0th element, it's or when I is equals to the last element. Okay, both of this is not true, because if the peak is the first element, it's going to work. Not a valid mountain array. If the peak is at the last element, it's also not going to work. So, but in the valid case, we reach the peak is at 6, right? So we still have to move on if in valid case, because we have to still go until the end. So let's just keep on going, but in this case, we walk down the mountain. Okay, we're no longer walking up, we walk down the mountain. And in this case, it's pretty simple. We just want to check it's smaller. Then we want to do I++. So if the next element is smaller than the current element, then we move, because we switch the condition here. So if 4 is lesser than 6, then we move on 3, lesser than 4, move on 2, smaller than 3, then we move on 1 smaller than 2, then we move. So because of just move one step forward, just do So until the very end, we just want to check, okay, until the very end, we want to check, is this pointer still at, is this pointer pointing at the last element? If it is pointing at the last element, right, then it will be a valid mountain array. If the pointer is pointing somewhere in the middle, it's not pointing at the end of the array, then it's not true. It's not true. So what we want to check here is we want to return fi is equals to array size minus 1, because we want to check whether the ice is at the last element, where array dot size minus 1 is last index. So basically this is a solution. It's quite simple. Check if reaches the end. Okay, so basically there are just these few conditions. So we want to try to walk up. So walk up, this is basically criteria number 2, and then walk down, this is basically criteria number 3, and then walking up, then reach the peak is basically criteria number 1. Yeah, so basically this is the thing. There's still some modifications we have to do to this code though. See the question. Is it possible for us to access the code session? Yeah, you can access it through the GitHub. I think later I post the GitHub link here also, then people can access. So yeah, so there's still one thing that we have to do in order for this to work. If I try to run this now, you'll see it will have it will give me an error. So let's just see the error, then see how we can fix it. And let's see what's the error is and how we can fix it. So let's just run this. It should error out. Yeah, it error out. So let's see what's the error. A bunch of gibberish. Okay, let's see. This is the useful information. Okay, here. So it comes here, it says heap buffer overflow on address something. Read of size 4, okay. This is not a meaningful message, but never mind, I'll just explain what's wrong here. So basically you can see that it's a runtime error. It says it's a runtime error. So the error happens at runtime. Why does the error happen is because we're trying to do i+1. So this will cause some error called array index out of bounds. So what is array index out of bounds? So imagine in this arrays, right? So let's say in this array, how many elements do we have? 1, 2, 3, 4, 5, 6, 7, 8. So we have 8. So let's say n equals to 8. Let's just make it more clear. Array.size equals to 8. In this case, array.size is equals to 8 because we have 8 elements. So when we try to do and then so the last element, so the last index will be 7 because we index array from 0, 1, 2, 3, 4, 5, 6, 7. So this is the 7 the 7 index. The index is 7. So when we try to do i+1, right? It is possible that we could do something like i+1, and then the I could be 4, which is 5, could be 5, could be 6, but it could be 7 as well, you know? It could be 7 as well. And if we try to index this, because 7 plus 1 is 8, so array at 8 element, it goes out of bounds because we only have 7 index here. We have 8 index, but the first one is 0. So 0, 1, 2, 3, 4, 5, 6, 7. There's no 8th index. If we index the 8th place, it will go array index out of bounds. It's not going to work. That's why you see some memory errors here, because the program is trying to access some uninitialized memory. So that's why there's an error. So how do we fix this? Is that we want to check that it must be smaller than 7. So let's say our array's dot size is 8, right? 8 minus 1 is 7. So I must be smaller than 7. That means the largest value that I can be 6. So the largest value when it is 6, even if it's plus 1, it will only reach 7, which is valid because we can index the 7. We can put a 7 as an index to this array. Yeah, so we just put this condition up, then it should just work. So for both while loop, we have to put that as well. So let's just run this again. And yeah, ta-da, you see that it works. So let's just submit it, and it should work just fine. Okay, so yeah, you see it worked fine. There's 39 milliseconds. So basically, this is the whole concept. This is the whole idea. And just to show the code that I had, that I ran test on. So basically, the person who asked for we have we will be able to access the code afterwards. This is the code that we'll upload to the GitHub repo. So in this code, it's basically very similar. I initialize I, and then I walk out, and then I reach the peak. Not pack. Reach the peak. Wait, peak doesn't spell like this. Okay, we reach the peak, and then we walk down, and then we check whether the pointer reaches the very end. So, but there's just one thing, that one optimization that I did here is I do a check. Okay, before we do everything, I did a check. I check whether if the array size has at least 3 elements. If it doesn't have at least 3 elements, it must be false, because like, you know, like, this cannot be a valid mountain array. What, like 1 and 2, which one is the peak? Peak is 2, and it must be at the very end. And if you turn it around, then it will be like 2 1, where the peak will be at the first element. So it doesn't work. It has at least 3 elements. So like this. So this is valid, whereas this is invalid. So this is a little check that I did. So it really doesn't matter too much, because in this case, the size is very small, so the computation can be skipped. Is not that much. So it can say, like, you can basically ignore this part. If you don't have this, it will still work. It's just that if you have this, it's a much clearer way of like thinking of the problem. So let's just run this. It should work just fine. Yep. So all the test keys pass. So basically, this is the solution to the problem valid mountain array. Is there any question for that? Okay, what if we write while array I smaller than array I plus 1 to walk up the array while array I bigger than... Yeah, that's completely valid as well. Like, it's basically the same thing. You are just turning around. Like, it will still work. Like, I can just prove it. It will still work, because whether you want to check the current array, whether you want to check the current element with the next element, or you want to check like the next element with the current element, it really doesn't matter, because they are basically the same. If I just run this, should just work as well. Yep, so it doesn't matter. So basically, that's it for today's problem. So one more thing is, before ending this session, I just want to do you all want to like explore some other questions using some other algorithm or data structures? Because like for the past 4 weeks, I've been just talking about arrays and arrays. Mostly of them are just arrays and strings. Like, how many of you do you think that we should introduce something new? At least for my side. Just maybe make a poll. Should we go deeper? Let's just ask. Maybe not like some very different question. Let's say, should we go for medium question next? I mean, one of us, maybe Macing or I, is preparing for medium question. So should we go for medium question? Let's just go. If you think we should go for medium question, we can just thumbs. Then we know. Okay. How many people do we have? 3, 4, 5, 6, 7, 10. We have 12 and then we have 9 volts. Okay. Seems like majority says that we should go medium questions. Okay, great. Then I'll talk with Mason about it. Then we'll see how we decide for whether we go medium questions. But if you have any other questions, you can just ask now. Else, I'm going to wait. One moment. I'm going to first, I'm going to commit the solution. Then I'll give you all the link to the GitHub for those of you that do not have the link. One more. Okay, so basically this is the link to the GitHub solution of every week. Yeah, so for those who are looking for solutions, you can for it here for every project has their solution here. So yeah, if you are interested to provide another kind of solution, actually if you go to look at the repo, maybe I share my screen. If you look at the repo, we have solution in C++ mostly, and we have one or two solution in Rust or Java. I think so. If you think you have, if you think you have like a different kind of implementation of different algorithms, feel welcome to create a pull. I think this is a public repo. Feel welcome to open a pull request, and then we'll see what added to it. If you want to try to say if you want to do practice and in another language, let's say we only have like solution in C++ or Java, mostly of them are in C++ lah. So if you want to provide a solution in Java or you want to provide a solution in JavaScript, Golang, any other language, you are welcome to open a pull request, and we'll Mason and I will look through it lah. Basically that's about it, and yeah, thanks all for today. Thank you for joining today. Bye everyone.